Hey everyone, I am making a video on how to find flux over a surface in 3 dimensions with a given force. So the big thing about the question that's being asked is that it's asking for upward flux. Upward flux means that the in hat, as drew on the surface, has to be pointed upward. It's pretty much the main thing of what it means. So this is only important whenever you're trying to do the integration and finding f dot in hat d sigma. That's where this in hat makes a big deal because it only really changes the sign of what your values are. And another thing that I didn't include on here, it asks to project this surface S, which is x plus 2y plus 3z equal to 6, across the zy plane. And I can demonstrate to you how I got to this part. So I want to go ahead and just show you. So looking at the YZ plane, x is going to be equal to 0. So we really have 2y plus 3z equal to 6. I solve for z because it's going to be like your y equals mx plus b type deal, where z is y is x. Kind of weird way of putting it, but that's how I see it. So z would equal negative 2y over 3 plus 6 over 3, which is 2. So this is really the equation. Solve for z. So as you can see, our mx plus b, so b being the z-axis, so the z-intercept, which is at 2. And this has a slope of negative 2/3. So for every 3 goes over, it goes down 2, which means our y-intercept is going to be 3. And so this is what it looks like when we're looking right here. See a little smiley face? We're looking down the x. And this is what we see in the zy plane. That gives you a better understanding of what we're looking at. So now we'll start getting into the math part of this. So the flux for a surface in 3 dimensions is going to be the double integral of f dotted with in hat d sigma. And the in hat d sigma, I'm going to draw over here to the right. I wanted to solve for all of this. N hat d sigma. So this is going to break it up into 2 different things. So n hat, which is the del f over the magnitude of del f. My bad. Sorry, for some reason my pen stopped working. There he goes. Because it's a unit vector, we're looking at the surface, the gradient of the surface. The unit vector for that. So the direction essentially of what is perpendicular, meaning the in hat, what direction is perpendicular to the surface, which should be the direction of in hat. So which is going to be del f over the magnitude of del f. Now this is being times by d sigma. D sigma is the magnitude of del f over magnitude, and for this case, fx. This can always change. This right here can change depending upon what your projection is. In this case, we have to project our surface into the zy plane. Since we're projecting in the zy plane, we have to use x here. So whatever variable you aren't seeing in the plane in which you are projecting your surface, that is the variable you put in your denominator for your d sigma. And then whatever variables you are using in your projection, you'll be finding that'll be your area, your dA. So just be dA of zy. So just a projection includes the axes of zy. That's why we have to use z. That's why we're doing dA, because we're literally finding this area here. I'll highlight it in purple. We're finding that area, but we're looking from the perspective of the x-axis, so we have to divide by fx. That's pretty much, we're finding the change, but we're taking out the change of fx because we don't really see that. It's doesn't matter to us. We care about the change that's happening with the area of zy. So to actually evaluate this, and just to show you, the magnitudes here cancel. So you don't have to worry about finding the magnitude of del f. You just have to worry about doing del f over fx times dA zy. So del f is really simple. Del f is just going to, you have to take your surface and make it equal to a function of x, but it has to be equal to a constant first. Since we already have up here x plus 2y plus 3z equal to 6, 6 being a constant, we can set this equal to a function. Whoa, might be. So this equal to a function, I'll stay away from that, f. So this is where we're getting our f from. So then we do del f, which is going to end with this being, or purple f at the top, that's being our f. So del f is going to be fxi, which is going to be 1i, plus fyj, which is going to be 2j, plus fzk, which is going to be 3k. Then we're going to divide by fx being 1, and it's the magnitude, so it has to be positive, so just in case it is a negative 1, you don't have to worry about it, it's just so it can be positive. So, and typically this fx, where they put at the bottom, is going to be 1, unless, and anytime it does have a variable in it, it is to help you simplify the problem more, or it's supposed to help you. It's supposed to be to your benefit to have something not be 1 in that, because it's trying to help you simplify it so you can it makes the math easier on you. And we have all of this, which is del f over the magnitude of fx times dA zy. So now we dot this with our f. So going back over here a little bit, so this would be dotted with our f. So f being xi plus yj plus zk. So you're really just multiplying your respective components, then adding them up together. That's what dotting does. So we'll have x times 1, which is plus y times 2, so plus 2y, plus 3 times z, so plus 2z. And since dA is included in that, we can all put, oh, whoops, I forgot to put my little double integrals with that. I'll put that over. dA zy. So since we are doing dA zy, we can have a certain variable in here, and that's x. We really hate x if you have dA zy. Or if you had dzx, you really hate y. Or if you have dxy, you really hate z. You have to eliminate that variable, which isn't included in your main area. So it's kind of discriminatory, but it's the only way that makes the math work. So we have to solve for x in terms of y and z with the surface that we're given, and plug it in. So if x, I'm going to do it at the bottom right here. So x would really be equal to 6 minus 3z minus 2y. So you plug that in. So we end up getting the double integral of 6 minus 2y minus 3z plus 2y plus 3z. And look at that. We will have just 6 in here because you have a negative 2y, positive 2y, negative 3z, positive 3z. So now we just have just 6 times our dz dy, or dA zy, however way you're going to put it. But we are, since our projection, it's not anything where we need to use polar. We can just now make this dA dz dy, and we'll solve for our limits. So I'm using dz dy, so I have to shoot my arrow upward in the direction of the positive z-axis. So we go from z equals 0 to z equals negative 2/3 y plus 2. And then we look at y. So y, we only care about the values when we enter and when we exit. So it would be y equal to 0 to y equals 3. So now we evaluate this flux. So you'll end up, so since it's just 6, we will, when we integrate this, we'll just get a z, and then we'll have 0 and negative 2/3 y plus 2 to plug in, dy. This will end up equaling 0 to 3, 6 times sorry about that. 6 times be 2 minus 2/3 y minus 0. I'm not going to include the 0. dy, multiply the 6 throughout. So then I go from 0 to 3 of 12 minus 4y dy. Now we can integrate y. So this becomes 12y minus 2y squared. From 0 to 3, this will equal, sorry, I forgot my y, and the 12. So it becomes 12 times 3 minus 2 times 3 squared minus 0. So this becomes 36 minus 18, which equals 18. Alright, I think that's pretty much it to the problem. Main takeaway from here is, I never explained to you all. Main takeaway from here, so since it's an upward flux, with the n hat being positive, we have to make sure when we find our f of x, it's like when we set this f equal to the surface, we have all of our values be positive, since it's being projected in a positive x, positive y, and positive z direction. So that was the importance of the upward flux. If it was the inward flux or downward flux, I think they would use downward flux, then we would have to make our surface negative. So if it asks for downward flux, downward, our surface would not be positive x. It would not be this. It would in reality be negative x minus 2y minus 3z equals negative 6, which equals f. So this would really only change our n hat d sigma, which would change the sign of the overall thing. So if we did downward flux, you would actually just get negative 18. Jesus. All right. You know what? Screw it. So the point of downward, looking at downward surface, is your n hat. And I will decide your direction. So take note of that. All right. I really hope this helps.